Good morning, everyone. Welcome back to the the last day of the first week of this workshop. So today, Melissa will give her second lecture on a mathematical introduction to the Amplituhedron.
All right, so I hope you remember what happened last time. I'm not going to do too much review. So, the thing in the background is this BCFW recursion for scattering amplitudes in terms of momentum twisters. We have these graphs in mind, which give you terms in these formulas, and we want to come up with some geometric space that's sort of encoding all of these different BCFW formulas at once. Okay, and so we already had these pictures, these Plabic graphs, and so we thought, okay, maybe we should just find a geometric space for Plabic graphs. So mathematicians had thought about that already. That was this totally non-negative Grassmannian, but it wasn't quite the right space. The graphs that we were interested in, they didn't decompose one piece of this space, right? They sort of corresponded to different pieces, and they were very low dimensional compared to the size of the space. So yeah, not too good. So we decided, or I guess the way I motivated the Amplituhedron was we want to squish this space so that our 4K dimensional cells, kind of having to do with the BCFW recursion, actually become full dimensional and fill the whole thing. So that's the idea. We need to squish the totally non-negative Grassmannian, and we do it using this Amplituhedron map. So just to remind you, what we do is we have our totally non-negative Grassmannian, and then we're going to pick a helper matrix Z, and it has some positivity constraints also, positive maximal minors. And this matrix Z defines for us a map which is just induced by matrix multiplication. So we take some point in the totally non-negative Grassmannian, so some k by n matrix, and we just multiply it on the right by our helper matrix Z, and this produces for us a point in a different Grassmannian, grk k plus m. And we talked about last time, so the dimension of this thing is k times n minus k, and the dimension of this one is k times m. And because of the way I picked n, k, and m, m is usually smaller than n minus k, so we've done some squishing. We've mapped a big space into a small space. Okay, and then the Amplituhedron is just the image of the totally non-negative Grassmannian under this map, this Z tilde map. And this is the notation that I'll use. Okay, and so, so hopefully you sort of remembered that. One thing that I want to say is, well, I'm not sure if I'll remember to keep this Z in the superscript here. It's supposed to remind you that to define this space, we do need this helper matrix. There's no way around it. I think everyone expects that the choice of helper matrix really doesn't matter at all. It won't change any of the story. And that's also mathematically what's been found so far. But I'll just, as a cautious mathematician, say no one's actually proved that. Like there's no proof that, sort of individual statements that we've proved don't depend on Z, but there's no guarantee that other things also don't depend on Z. Okay, so, but now I'm gonna kind of probably ignore the choice of Z for most of the time. Okay, so that little caveat aside, the first thing I want to do, so today what we'll do is we'll kind of delve into what geometric statement do we want to, precise geometric statement do we want to say about the BCFW recursion in this space? So that's where I'll get, go ahead. The maximal minors are all positive. Yeah, that's all you need. That's all you need. Yeah, so it's it's some full dimensional subset of this matrix space, but it's sort of you should sort of think of it as being sort of like a little subset like this, not like most of the space or anything. Okay. Yes. No. So yeah, this map, you would hope that since you've got a bunch of positive things over here, it sort of doesn't mess with positivity that much, but actually the signs of the Plücker coordinates here are very hard to predict. And I'll introduce some other coordinates that are different than Plücker coordinates that are kind of better suited to analyzing this points in the image. Yeah, they're the momentum twisters, as a spoiler. Okay, yeah, so I think that means that I should do an example so we can kind of get a feeling for what this map looks like. So kind of the easiest example to do is k equals 1, m equals 2. So the physically relevant one is m equals 4, but m equals 2 is easier to get your hands on. Okay, so in this situation, my matrix Z is going to be an n by 3 matrix. Oh, geez. There we go. There we go. Yeah, sorry, I did the wrong thing for the matrix multiplication. Makes sense. Okay, so yeah. So it's going to be an n by 3 matrix. Yes.
When you say physically relevant is the m equal to 4, so when you look at m equal to 2, did you have to do anything additional on the left-hand side on the grk comma n, or the same on-shell functions take you to m equal to 2 as well?
Yeah, so the m only changes, well, it changes the size of your helper matrix, and it changes what kind of Grassmannian you land in.
Okay.
But the domain of this map, the thing you start with, doesn't see m at all. You just always start with the totally non-negative
So the
Grassmannian.
physical on-shell functions still carry information about m equal to 2 as well. Is that right? On the left side?
Yeah, anything over here you can port into the amplituhedron for any m.
Thanks.
That's right. That's right. Okay, so why is this the simplest situation? Well, let's think about the amplituhedron map. So it goes from grkn, so that's totally non-negative grkn, so that's totally non-negative gr1n. We like that space because it was straightforward. This was the simplex in p to the n minus 1. Okay, and then where does it go? Well, it goes to grkk plus m. So in this case, that's gr1, 3, which is just the projective plane. So that's why this map is simple, because we are starting from a simplex, and we're just sending it into the projective plane. Okay, and so just really concretely, what are we doing? Okay, so I pick a point in here, so that's the row span of just one vector, right? It's just going to be a line. And since I'm in the totally non-negative Grassmannian, all of my coordinates in this vector, I can take them to be non-negative. Okay, and then I just multiply by my matrix Z, and if I write it in terms of the rows of Z, what I get is x1 z1 plus x2 z2 plus xn zn. Okay, so what's happening here? Well, okay, these rows of Z, right? They have 3 entries, so I can either think about them as being a vector in R3, or when I think about their line, I think of them as being a point in P2. Okay, but let's think about these. This is like a linear combination of vectors in R3. So what I'm doing is, I'm taking these vectors, the rows of Z, and I'm just taking all non-negative linear combinations of those vectors. Right, and so when you take non-negative linear combinations of vectors, oh, this is going to be kind of hard to draw. What you get is a cone, right? A cone in R3, a convex cone. Okay, and what I'm doing to think about it in P2 is I'm taking my convex cone and I'm just kind of slicing it somewhere. I'm not going to be able to draw this, so let me just show you the picture in P2. The picture in P2 looks something like this, where my vertices here are given by the rows of Z. And then I also get all of this stuff inside of this polygon, kind of by changing, right, by varying my x's over all non-negative numbers. So, right, 2 comments here. You might wonder, like, oh, couldn't some of the rows of Z sort of end up inside of this picture? And I kind of drew them in a particular order where I kind of saw them in order going counterclockwise. And right, both of those things are guaranteed by the positivity of the maximal minors here. So because my maximal minors over here are positive, all of these rows of Z will really be vertices, and they'll show up kind of in this counterclockwise way. Okay, that seem okay to everybody? So in this very baby case, all we get from the amplituhedron is a polygon sitting inside of the projective plane, and the vertices I just read right off of the rows of Z. Okay, and this is, okay, so this phenomenon kind of, that I got a polygon or a polytope, that's a little bit more general. So if I demand that k equals 1, but let m be arbitrary, then I still have this situation where the z tilde map is going from a simplex into projective space. And right, this is basically a linear map. So if I hit a simplex with a linear map, I should get a polytope out. And that is indeed what happens. So in this situation, the amplituhedron, sorry, k is equal to 1, is what's called a cyclic polytope. In PM. And this, okay, it wasn't phrased in this language, but actually is a result of Sturmfels from the 80s. Okay, and what do cyclic polytopes look like? All right, I have a picture drawn in my notes. We'll see. Okay, I'll try to give you an example of a 3-dimensional cyclic polytope. See how badly I fail. So. Yeah, while I draw, maybe I'll say cyclic polytopes come up really naturally in combinatorics. So this is a nice class of polytopes that mathematicians like to study totally away from any connections to scattering amplitudes. And so it's sort of nice from a mathematical perspective that they just show up naturally in this setting. Okay, so this is the sort of picture you get if you chose m to be 3 instead. And again, you see that the vertices are exactly the rows of z, and they sort of go in a counterclockwise way. Okay, so that's one nice situation. So when k is equal to 1, we just see something that's totally linear and combinatorial. Oh yeah, go ahead.
Yeah, sorry. Can you say a bit more? What's the difference now with respect to the previous case?
Okay, so this was m equals 3, and I guess I drew the n equals 6 picture, and this lives inside of P3 instead of inside of P2. I guess, yeah, so, well, polytopes in the plane are really boring. You can't really, there's just one kind. But in 3 space, you get many, many different options. And these particular polytopes, these cyclic polytopes, are very special because they have the most possible faces in each dimension, given the number of vertices. So they're sort of a maximal, yeah, they're an example of sort of a maximal combinatorics. Which vertices are going to? Yeah, that's right. So this is in 3 dimensions. So sorry, this stuff is in the back. Yeah, so this is part of there's as many faces as possible in each dimension. So you want to have kind of as many edges as possible, as many 2-dimensional faces as possible, et cetera. So yeah, that's sort of the kind of behavior here. Yeah, 1 does indeed go to everything. No, I guess there's no edge between 2 and 4 or 2 and 5. Oh, well, okay, so the rule is you take the convex hull of the rows of Z, and because you had positive maximal minors, this is the sort of picture that you get. Yeah, so yeah, I'm not sort of giving you all the details, but you could actually very easily come up with this polytope, yeah, if you wanted. Ah, you're asking about the name, why it's called a cyclic polytope? Yeah, so there's no, it's not a cyclic polytope because it has cyclic symmetry. The cyclic here is for some other reason. Yeah, was there another question? Yeah, so let's do this example. So here, my matrix is an n×3 matrix, and I'm gonna call my rows Z1 through Zn. And each row gives me a vertex of my polygon. Really, yeah, so if this is the origin down here, if I draw these lines, this vector from the origin to here, that would be like the nth row of Z, right? Because that's a 3-dimensional picture. And so then what I'm doing is I'm taking that cone and I'm slicing it And so now my lines turn into points, but still the vertices correspond to the rows of Z. Yeah, so this is like a going from R3 to P2 sort of thing. Does that make sense? Okay. Yes, that's right. No, some stuff goes inside, right? So this this polygon, we got it by taking like an n-1 dimensional simplex and projecting it down to the plane. N-1 dimensional simplexes have tons and tons of edges and faces and facets, et cetera, and they all kind of, most of them disappear in this picture. Yeah, so it's a very violent thing, you know, the squishing, yeah, so this is maybe a really good example. The squishing that we're doing is very extreme. It kind of messes a lot with like the boundary structure here, maybe doesn't have too much to do with the boundary structure down here, and that's actually one of the things that makes like the Amplituhedron a very difficult thing to work with, because you have to be really careful or to deal with the effects of this squishing. Okay, right, so this was a nice situation, k equals 1, everything is linear, we have good combinatorial understanding. Another situation where everything is linear and we have good combinatorial understanding is m equals 1. So this is Karp-Williams. And I'm not really going to give detail, I'm just going to say the m equals 1 Amplituhedron is also linear. Okay, and maybe I'll say it's the bounded complex of a hyperplane arrangement. Okay, and I don't want to say more about this. I just kind of want to emphasize in this other extreme case, when I set the parameter m equals to 1, we also know what's going on. We know what's going on with the combinatorics. Everything is good. I guess, okay, I wasn't going to say this, but maybe I will. So in work with Parisi and Williams, we show that the m equals 2 Amplituhedron, well, it's not linear, but somehow it has kind of some linear features. So what I'll say is it's not linear, but it behaves like a polytope. Okay, heavy quotes here. I'm not going to tell you what this means. It's just to say, okay, m equals 1 is really nice. M equals 2 gets a little bit more complicated, but still is pretty nice. And then after this, everything is kind of crazy. So m greater than or equal to 3, the Amplituhedron is curvy. No, this is arbitrary k. Right. K equals 1, arbitrary m and n, really easy to understand using polytopes. And so now we're thinking about different extremes. So yeah, lowest we can go with m is m equals 1. That one's also not too bad. One step up, okay, still we can understand it, mathematically well behaved. Beyond that, we have some results, but definitely like are far from a complete combinatorial understanding like we have in this case. A simplex. That's right. Yeah. So this, what I'm saying here, like behaves like a polytope. What this means is that I have another polytope which encodes combinatorially all of the behavior of the m equals 2 Amplituhedron. But it's sort of an analogy only at the level of combinatorics, not at the level of geometry. Yeah, I'm happy to tell you more about this later, but it's sort of aside from the point of this BCFW stuff. Okay, right. Yeah, so, okay, I'll finish the sentence. Okay, and yeah, I mean, yeah, maybe I'll just leave it here. Okay, so now so I've given you the survey of sort of the easy Amplituhedron to picture. So now let's return to our kind of original question, which was m equals 4 Amplituhedron is supposed to encode the BCFW recursion in some way. So yeah, so now we'll focus on m equals 4. Okay, and I'm going to just remind us what we actually wanted from the Amplituhedron. Okay, so what we wanted is that it should be covered by some pieces which reflect the BCFW recursion. Right, that's all of our different BCFW formulas. We want them to tell us some way to break the amplituhedron up into pieces. Okay, and right, and so, yeah. So I think it's because space-time is four-dimensional. So the 4 is the same thing as that 4. Yeah. Okay, so covered here means, yeah, my pieces should be full-dimensional. Right, so we should think back to this analogy like Hodge's, the schematic, right? You understand the volume of the square by breaking it up into triangles in different ways. So that's the sort of thing we're doing here. So when we cover things, we want our pieces to be full dimensional and they shouldn't overlap. And our pieces, well, this is a little bit, like the intuition should be, like, we had these graphs, right? They gave us positroid cells. And the positroid cells weren't the right geometric object to look at, but somehow the pieces down here, they should still sort of come from those same graphs. So maybe what we want to look at is we just want to take one of those positroid cells and we just want to push it down into the amplituhedron, right? So maybe our pieces should look like that. Right, so these are images of positroid cells. Okay, and then this reflects the BCFW recursion part. I guess there's kind of a few different ways to interpret this. The most basic one is just like, if I give you a BCFW formula and I sort of look at those pieces, then I should really cover the whole thing. A more refined thing to say is that if I look at the forms associated to all of those pieces, I should be able to recover the actual BCFW formula. Okay, so I'll just say, maybe I'll say something like, we would hope that something like the volumes of the pieces we're using, oh, actually, let me introduce some notation. So ZG means the image under the amplituhedron map of the cell SG. Okay, so what we would want for this to reflect the BCFW recursion is that the volumes of our pieces, these ZGs, should give us terms in these BCFW formulas. Okay. So this is sort of what we're hoping for. Any questions? All right. Okay, and so now I'm going to rewrite basically exactly the same thing, but I'm going to write it in more mathematical language. Yeah. Probably the only person who benefits from this is me, because I'm, oh yeah, go ahead.
Yeah, I'm just wondering, I mean, this sounds very good. Maybe the last requirement, I mean, my feeling is that maybe that could be optional, because, I mean, would be even more interesting if you found a different type of representation of the answer.
Yeah, I mean, I will say, I myself and mathematicians generally, I think, have actually like focused kind of more at this level. And then some of our results sort of suggest that like something like this maybe should be true, but actually I don't know if anyone has like checked it really carefully. Yeah, the other thing that I'll say is I'm going to start writing some stuff down, and it will make it clear that it will make it clear the way you generalize this sort of actually away from the BCFW recursion, just to decomposing the amplituhedron in a nice way. And you would expect all of those decompositions, yeah, to give some formulas for scattering amplitudes that are somehow non-physical, don't come from this BCFW recursion. Yeah, so that's a good point. Okay, anything else? Okay, so those properties, more or less, are kind of the reasons, this goal was basically the goal of Arkani-Hamed and Trnka when they defined the amplituhedron. I mean, translated into my words, so don't quote me. But yeah, so I'm going to say what they conjectured basically is that if you have one of these BCFW formulas, so I'm going to write this as like the amplitude is equal to some sum of graphs, G1 all the way up to GR. Okay, so what they conjectured is if you have one of these formulas, then this positroid cell image, right? So I just pick the positroid cell corresponding to this graph and I hit it with the Z tilde map. That image should be full dimensional. So in this situation, that's 4K dimensional. And the Z tilde map is injective on the positroid cell. Okay, so I'm going to write all of the things and explain them. So that was the first part. And then the second part is that if I take two different ones of these positroid cell images, right, from kind of coming from these graphs, they don't overlap. And if I take the union of all of these positroid cell images, I cover the whole thing. Okay, and I should close one side. Right, and then this last one, this sort of, not sure if it's a requirement or not, you kind of want something like the form of these positroid cell images gives the correct term of the BCFW formula. Okay. So I've basically just taken what I had over there and written it kind of more mathematically. There's one new thing that has happened, which is that I asked for this condition that Z tilde is actually, oh, I'm sorry, that didn't make sense. I asked for the condition that Z tilde is injective on this particular positroid cell. So injective means one-to-one. So what it means is that the Z tilde map is actually not doing any squishing on that particular cell. So if you take the whole totally non-negative Grassmannian, the Z tilde map is necessarily going to squish some of it. But this is saying, well, if we look just at the correct small piece of the totally non-negative Grassmannian, the Z tilde map is just moving it kind of undisturbed downstairs. Okay. Yeah, go ahead. That's right, that's right. Yeah, so these are very special positroid cells is the answer. They're sort of exactly the ones that come from these BCFW formulas. And so in particular, these positroid cells themselves are 4K dimensional. So at least there's like a chance for this to happen. Yeah, so the way you should think of it is going back to this picture, this polygon, we had a very high dimensional simplex upstairs. We projected it down. Most of the boundary structure of that simplex got messed up, but there's some edge of the simplex which actually just got mapped to this exact edge. Okay, so most of, yeah, bad things happen to most of it, but if you just looked at these particular n edges of the simplex upstairs, they just map down very nicely downstairs. That's sort of the picture you should have. Okay, so why would you want this? Why did I add this condition? This is not a condition that I sort of had over there. Well, I can give you two answers. From a mathematical perspective, this is natural, because if the Z tilde map is just kind of taking this cell and just like moving it down undisturbed, that means that this positroid cell image is just as nice as the positroid cell upstairs, right? So it remains very simple, it's just a ball. The other reason you want this is that as soon as you have this, you can use the Z tilde map to write a form on the image using the form from the domain from upstairs, right? Yeah, I'm not going to go too much into detail, but I'll just say this is the condition you want. If you want a form upstairs to be sort of interpretable also as a form downstairs. So that's another reason why it's a natural condition. Okay, any other questions? Yeah, okay. So let me decorate this a little bit. Yeah, okay, maybe I'll do this on the side. So I'm going to call, okay, so I keep saying positroid cell images, but right now we actually only care about like pretty special positroid cell images, kind of these ones, right, where the image is 4K dimensional and Z tilde was injective on the cell. So I'm going to call those tiles. Those are the ones I care about particularly. Okay, so I'm going to call ZG a tile if, well, really the first bullet point holds. So it's 4K dimensional and Z tilde is injective on the cell SG. And then a collection of tiles that don't overlap and cover the amplituhedron, I'm going to call a tiling. Right? I'm fitting together the tiles so that they sort of cover the whole space. Yeah, go ahead. Yeah, so the reason that I need to ask that they cover is because I'm really not taking all positroid cells when I'm doing this, right? So the ZGI, they're like some very special positroid cell images, and I don't know, yeah, I don't know a priori that I've taken enough of them. Yeah. Yeah, I'm taking a very small subset of the cells upstairs, and then I'm looking at their images downstairs. Yeah, and they're very far away from covering the whole thing upstairs. Yeah, yeah. Okay, so the kinds of positroid cell images I care about are tiles, right? So what I'm saying here is that all these GIs, they should give me a tile. And then I'm also saying that any BCFW formula, it should give me a tiling. So if a collection of tiles is non-overlapping and cover the whole amplituhedron, I call that a tiling. Okay, so the short way to phrase points 1 and 2 is, right, so yeah, so let me just like write this conjecture another time, right? So this conjecture, just using this language, is saying that for a BCFW formula, right, so amplitude equals G1 up through GR, the conjecture is each one of these graphs gives me a tile, and 2, the collection of all of these graphs in the expression give me a tiling. Okay, and then, yeah, 3 is not translated in this at all. It just stays 3. Okay. So all I've done is introduce mathematical language for this, basically. The advantage of this mathematical language is now we start to see, oh, okay, yeah, so the conjecture is that BCFW formulas should give you tilings. But now we see, yeah, this opens up the door. Maybe there's more tilings. So maybe there's some ways of decomposing the amplituhedron into these tiles, these positroid cell images that just don't come from the BCFW recursion. And in fact, that's true. I think it's a really interesting direction of research. I can't tell you that much about it yet, so I'm just going to stick with BCFW for the rest of the talk. Yeah. That's right. That's right. Yeah. Yeah, every tiling is going to come from some 4K dimensional positroid cells upstairs that I just move down undisturbed downstairs, and then they cover the whole thing. Okay. So unsurprisingly, maybe running a little bit behind time. Maybe what I'll do is I'll talk through what the tilings look like over here, maybe without writing down as much as I ought to. So over here, yeah, maybe I'll do another color so it's visible. Okay, so in this situation, okay, yeah, the other thing is I wrote everything for m equals 4, so you should imagine if I wanted to do it in general, then I would just change the 4k to m times k, and then I would put an m here instead of a 4. Okay, so yeah, in this situation, the easy one, m is going to be equal to 2. And so, okay, these tiles, they should be images of positroid cells that are full dimensional, so 2-dimensional, and the z tilde map should be injective, so it should just kind of like move it down without squishing it at all. Okay, what does a 2-dimensional cell up here look like? Well, here's an example. If I take matrices that look like this, which just have 3 positive coordinates and all the rest zeros, that will give me a 2-dimensional cell. You should remember we're in projective space. Okay, so I take this and I map it into here. And what do I get? Well, when I do this matrix multiplication, I'm just getting some linear combination of z1, z2, z3, right? Nothing else. And so I land somewhere inside of here. And in fact, as I vary x1, x2, x3, I'm going to vary over all points inside of this triangle. Okay, so I took any 2-dimensional cell up here, I mapped it down, I see that I get something 2-dimensional. And now I have to think, okay, when is the map injective? So when can I go from here and recover a unique point up here that mapped down to it? And the answer is, well, actually always. So if I pick some point in here, I can write it as a combination of z1, z2, z3. And that's going to give me the x1, x2, x3 from over here. And you have to think a little bit, there's like some freedom on both sides because we're kind of projective over here and projective over here, but it matches up. So in this situation, okay, right, so I said a tile is the image of a positroid cell where the z tilde map was injective. And so my tile here is actually just going to be this triangle. Okay, so tiles are just going to be triangles that are like convex hull of zi, zj, zk. Okay, so tiles are just triangles. And then tilings, well, I'm going to decompose my whole polygon into a bunch of non-overlapping triangles that cover the whole thing. So what's that? It's just a triangulation. Okay, and actually in the physics literature, you'll often just see triangulations of the Amplituhedron. As a mathematician, I don't like that so much because usually we don't have triangles. Okay, fine. Yeah, in this case, we actually, tilings are exactly the same thing as triangulations. Very similar situation with other k equals 1. We'll just get triangulations of cyclic polytopes. Yeah, but for other for other k, you're not going to have something linear. You're not going to get your pieces or simplices. Yeah. Okay, yeah, go ahead.
Yeah. So if we just think about this this picture, one might be tempted to put another, let's say, C star in the middle and then have some other tiling. Would there be some way of thinking about such other pictures where you have additional points which are not in the original kinematic data?
You certainly can. This exact framework won't tell you about it as nicely. So like here, if you wanted to put this extra point in, maybe you'd be looking at a decomposition that looks like that. And we just saw that the 2-dimensional positroid cells, they don't really give you pieces that look like this. Instead, they give you triangles where the vertices are the vertices of the polygon. So to hit some region like this, you'd need to take some subset of the positroid cell, which is not too bad. Like maybe that's a reasonable thing to do, but it's sort of not quite as natural from the perspective of this like positroid decomposition of the totally non-negative Grassmannian. Yeah, so I would say you certainly can think about that. Somehow the technology of positroid cells doesn't know about these decompositions as well, so it would be a bit more complicated. Yeah. yeah, there's some more things maybe to say in that direction, but maybe I'll refrain. Any other questions? Okay, so we have formalized this notion of the amplituhedron reflecting the BCFW recursion. We saw that the definition we came up with, at least it gives us something reasonable in sort of a different situation. So, okay, we think it gives us, hopefully it gives us something reasonable for m equals 4 also. And I guess the next thing I'll tell you is this conjecture is, at least parts 1 and 2, are rigorously mathematically proven. So, yeah, maybe I'll write it like this. So, theorem, so 1 and 2 are true. Like, I think no physicists were surprised about this, but mathematicians felt good about proving it rigorously. Yeah, and so I should say, so 1 and 2 were proved for the nicest way of running BCFW, so kind of for a single formula by Ivan Zohar, Zvika Leclerc, and Ron Tesler. And then with those authors, together with myself, Matteo Parisi, and Lauren Williams, we showed the kind of full generality of 1 and 2. Oh gosh, there's so many names in this, I'm gonna forget somebody. Okay. So, seems good. We formalized our notion, and in fact, it is correct. So the amplituhedron, like everyone now should believe, it really is the object, an object that encodes this BCFW recursion. I'm going to spend the rest of my time kind of talking about digging in a little bit more into what we do and what we discover from this proof. So maybe this doesn't feel too exciting that 1 and 2 are true because like we really, really believed it. But we also actually get more information out of the way that these things are proved. So I'll try to get there. Okay, so how do we, I'm not really going to talk about how it's proved. I'm just going to talk about kind of the key idea. I'll do this. Okay, so the key idea of this proof is basically, we can see from this picture, okay, so the way I defined tiles was, okay, images of positron cells where the Z tilde map is injective. The key idea of that proof is that's a really bad way to think about tiles. The much better way to think about tiles is as, you know, in this situation, triangles, right? That's much simpler. So yeah, the key idea here is sort of to get rid of this totally non-negative Grassmannian in the description of these tiles. So what that means is the very first thing we want to do is we just want to describe these positroid cell images as a semi-algebraic subset. So just talk about what do they look like inside of GRKK plus 4, which is where they live. So the kind of description we'll do is we'll say, okay, these tiles, they're just those points in GRKK plus 4 where certain polynomials are positive. Okay, and you need 5K polynomials, it turns out. Okay, and they're not polynomials, or it's the easiest way to write them is not as polynomials in the Plücker coordinates, but as polynomials in the momentum twistors. So that's what these mysterious IJKL brackets are. Those are momentum twistors. Right, and then these polynomials, right, so I should say they're a pretty high degree usually. Okay, and what this sort of thing is good for is, well, you can kind of just imagine, like, this is a much easier thing to think about than having to deal with all of the stuff about positroid cells and this complicated map in the background. So once you have this, it's much easier to prove things like the tiles are non-overlapping, right? Because we sort of have an inequality description. It's also easier to prove things like the whole space is covered. Another thing, though, actually, that this is very good for, so we use this, is having such a description actually helps us invert the z tilde map. So it helps us go backwards. And right, and I also said, okay. And yeah, so I guess I'll just tell you, like, how does this help you invert the z tilde map? Well, we had this sort of, how did we describe points in positrade cells? We picked some edge weights and then said you run boundary measurement, and that gives you a point in your cell. The edge weights that you should pick are just exactly these functions, right? And so that's, yeah, this just sort of directly tells you, how do you go backwards? What edge weights do I pick to get the point upstairs that maps down to this one? I just picked these edge weights. Yeah, go ahead. Yeah, so this is a good question. Like, how am I producing these? Why are there 5K of them? The answer is there's a recursion. At each step in the recursion, you add 5 polynomials to your list, and the recursion goes like k many steps, whatever your k is. So that's how you end up getting 5K. I will give you more detail in 1 second. The one thing I want to, yeah, so I'm about to go into more detail about what these Fs are and what these momentum twisters are and stuff like that. Before I do that, I just want to say, using this semi-algebraic description and how to invert the z tilde map, you can get kind of as a corollary that a reasonable form to associate to ZG is just the D-log form of all of the Fi's. Essentially, I'm lying to you a little bit. Right, and this just goes back to the positrade cells themselves had natural forms, and then these tiles are exactly the same thing as the positrade cell. I've just hit it with z tilde, and so then I can invert everything and use that inversion to write a natural form on the bottom. Okay, so yeah, I guess before I give you more detail on this point, I just kind of want to emphasize, like, this proof, going through and actually showing really carefully that these are tiles, it tells us exactly what one natural form on these tiles is, which seems like a good thing to know. Yeah, go ahead. That's right. Here to there? It's pretty hard. I think that we haven't like done it precisely. So yeah, somehow, I mean, for the Amplituhedron, you don't need high degree polynomials. You just need like just some momentum twisters. Yeah, and that's like pretty hard to see from here. There was another question, yeah.
Is there any physical origin for those FIs or?
Sort of. Maybe this is a good time for me to switch to my slides so I can show you how you actually obtain them. I don't actually know how to. Okay, he assured me I could just say switch to slides and then it would happen soon. So we'll see. I might be able to do it also. Okay, I don't think I did anything. I think that was all. That was entirely coincidence. Okay, so yeah, how do we get these FIs? The question is, can I? Okay, so it's recursive in general. We have some explicit formulas in the like nicest way of running the recursion, but yeah, in general it's recursive. So basically, in the BCFW recursive formula, there were sort of 2 kinds of terms. One kind of term looks like this. And in this situation, the FIs you use for the big graph are just exactly the same as the FIs you use for the small graph. Okay, so no change. Then there's this more complicated picture where we had sort of this like butterfly in the middle, and we stick on these like 2 smaller blobs that come from lower k and n. And in that situation, what do you get? Okay, so, I'm too quick. Okay, so one thing that you get, okay, so this butterfly, it touches 5 external legs, which I'm going to call A, B, C, D, N. And some of the functions, 5 of the functions you get are just momentum twisters, kind of using 4 out of the 5 of those indices. Okay, and I'll tell you in a second what this actually means. And then some of them come from the FIs you had for the left graph, but you do a little substitution. Every place that you see a B, so that's actually like a ZB, you replace it with this linear combination of B and A, an adjacent column. Okay, and then for the right, something very similar. You take all of the FIs for the right graph, but then you shift them a little bit. You shift D with some linear combination of D and C, and you take N and you shift it with a little bit in the direction of N, D, and C. Okay, and yeah, I'm sorry I went out of order. Let me actually tell you what these symbols mean, these brackets. I'll give you the mathematician version. You have to ask a physicist for the physics version. So, yeah, okay. So, okay, so I have these functions, these bracket A, B, C, D. So these are functions on some point in GRK k plus 4. Right, so I've got some point in GRK k plus 4 where the amplituhedron lives, and I pick some indices I, J, K, L in 1 through N. And I also have in the back of my mind my amplituhedron matrix Z. Okay, and I'm going to use this data to define some functions on Y. And if I haven't screwed anything up, this is honestly a momentum twister if you view it the right way. Okay, so what is it? So I'm going to denote it by bracket IJKL. And it's just going to be the determinant of the matrix where I put Y on the top, and then row I of Z, row J of Z, row K, and row L. Okay, so Y, remember, is in GRK k plus 4. So it's got k plus 4 columns and k rows. And then I've added on an extra 4 rows. So this is really a square matrix, and I can just take its determinant. Yeah, I'm not going to tell you how to get the momentum twisters you're used to from physics. You got to ask someone else for that. Okay, so these are the functions that I'm dealing with. They're linear functions in the Plücker coordinates of Y, so they make a lot of sense still. But these are the best coordinates to use to phrase, for example, this recursion. Okay. Any questions? Okay. So if there aren't questions, sorry, maybe the information density picked up a little bit in the last little while, so please feel free to slow me down. Let me show you, in the meantime, an example. So how does this work? So, oh yeah. Yes. Yeah. Yeah. So my Z matrix looks like Z1 through Zn. So I'm sticking in some rows of Z. Yeah. And this should be a 4. Yeah. And there's some way of kind of projecting out the Y somehow, and then I think you get into like actual momentum twisters that you're used to. Okay. Any other questions here? Okay, so yeah, maybe I should have done this before. Here's an example. So I'm doing one step in the recursion, so I'm going from some little left graph and little right graph to some bigger graph. Okay, and so for this little left graph, this came from just having the core and blobs that were kind of empty. Okay, and so I just get these 5 momentum twisters, which they just use, each one uses 4 out of the 5 indices of this core. Okay, and then very similar for the right, I have this like extra dangling lollipop, so that doesn't matter at all. All that matters is sort of the 5 indices involved in touching the white vertex. Okay, and then I'm actually interested, so these functions, yes, I'm doing a trick with the signs. If I multiply these functions by the signs right above them, then that cuts out exactly the tile associated to this graph. Okay? And now I want to go from knowing the inequality descriptions for these two smaller tiles and like a smaller amplituhedron to knowing the inequality description for this bigger tile in a bigger amplituhedron. And all I do, okay, so I have this core part, this butterfly. It's on indices 3, 4, 7, 8, 9. So I pick up the 5 momentum twisters on those 5 indices. Each one has 4. And then I also need to take the momentum twisters I had up here, and I need to change, I need to do some shifting on, I guess on 4. 4 is what I should mess with. And is that actually reflected? Yeah, so if 4 and 3 appear together, then nothing's going to happen. So that's why nothing happens over here. If you just stare long enough at exactly how you're shifting, 3 and 4 appearing together means nothing happens. So the only thing that happens is in this one when 4 appears without 3. And then I do that thing where I'm going to shift 4 to a linear combination of 4 and 3 with some coefficients. And so when I do that shift, I get this polynomial in momentum twisters instead. Okay? And then very similar up here, now I'm going to do a more complicated shift where I shift both D, which is 8, and N, which is 9. And so again, some momentum twisters stay the same, but then some turn into these quadratics because of this linear combination that I'm doing. Okay, and I'm hiding from you how the signs change, but that's also predictable. Okay, so this is how this recursion works. Yeah, go ahead. Yeah, so they're predictable. If I had written them both in the right way, it would have been alternating plus, minus, plus, minus, plus. So sorry, I should have swapped the order of those two things. Yeah, so there's, what I should say is the signs for k equals 1, you can just figure out. And then there's a prescription for how they evolve. Yeah, sorry. The real stuff, yeah, the precise thing is in our paper, so you can look there. Okay, so great. I have a semi-algebraic description for this. It's recursive. Maybe that doesn't feel like such a good thing, but one thing that is good is that our recursion, the recursion we're doing here, matches exactly with the momentum twister BCFW recursion from the all-loop BCFW paper. So as a mathematician, I shamefully don't know all the physics behind that recursion, but whatever the physics is behind that recursion, it's the same as what's happening in our recursion, right? So we are doing the right thing. The geometry is really matching up with what it should on the physics side. Okay. The other thing I want to say is right, so now we're at kind of a place that maybe it doesn't feel so good because, yeah, we have the semi-algebraic description, we have these FIs. They're very important, for example, in writing down the form, but we only have a recursive description for them. So that doesn't feel so good. Yeah. Mm-hmm. Yeah, so the new 5 comes from the like butterfly in the middle, right? The new 5 are these ones. And then there are 5 times KL of the left FIs and 5 times KR of the right FIs. And KL plus KR is K minus 1. Okay. Yeah, so recursively, each time you put in one of these cores, you're both increasing K by 1 and you're increasing the number of functions you need by 5. Okay. Yeah, okay, so maybe we're in a situation that feels a little roughly like kind of the Feynman integral situation where you have something that's maybe actually really hard to compute, but you know you'll get some functions in the end, and you want to say, well, what do we know about those functions? Can we say they live in this class? And that's what I'm going to tell you next. So this is kind of the biggest new thing that came out of this proof, is that the FIs that we're using are very, very, very special polynomials in the momentum twisters. They're not random. They come from something called the cluster structure on the Grassmannian 4n. Okay, and I'm not expecting you to know what cluster structure means, so I'm going to tell you a little bit what that means. Okay, so the cluster structure on GR4n has to do with functions, so it has to do with the Plücker coordinates. Okay, so I'm just going to use some notation, this C GR4n. This just means the polynomials in Plücker coordinates modulo the Plücker relations. Okay, so these are the polynomials in Plücker coordinates that sort of make sense as functions on the Grassmannian. Okay, and okay, so that's one definition of this ring, just polynomials in Plücker coordinates mod Plücker relations. But this ring, or this algebra, actually has a really special structure called being a cluster algebra, which is a totally different way of writing down an algebra. Okay, so the way that I just told you about this algebra up here was I said, okay, it's generated by all of the Plücker coordinates. I'm just taking all polynomials in Plücker coordinates, and then I have some relations among them that I'm gonna mod out. For a cluster algebra, what I'm gonna do instead is I'm gonna kind of grow it from a seed, which is gonna be a very small subset of the generators, and then I'm gonna tell you how to get all the rest, and I'm never really gonna tell you relations, they're gonna be built in. Okay, so what's a seed? It's a picture that looks like this. So it's two pieces of information. Underlying, the kind of underlying combinatorial information is a quiver. So that's just a directed graph, so it's a bunch of like vertices and some arrows between them. And then there's also some algebraic information, which is that on top of each vertex of my quiver, I'm gonna put a polynomial in the Plücker coordinates. Okay, and here actually I'm just putting a Plücker coordinate on top of each vertex. So I'm just writing the indices, but you should think of this as the Plücker coordinate delta 3, 5, 6, 7. Okay, so that's what a seed is. It's just a quiver, this decorated graph, this directed graph, and on top of each vertex, I'm gonna put a particular polynomial in the Plückers. And I'm not gonna tell you how I cooked these up, but I can't do it randomly. I have to do it very specifically in this way. Yeah, so I'm going to give this particular seed, I'm going to give it a name. It's the box seed because it looks like a box. And something that's very important is that this collection of Plücker coordinates actually gives me a concise coordinate system for the Grassmannian. So these are algebraically independent. There's no relations among these, and there's just the right number of them. There's dimension many of them. So this kind of answers your question before. This is like one choice of non-redundant coordinate system. Okay, so this is the input for a cluster algebra. This is a seed. And then, oh, and I should also say the functions that I decorate the vertices with, I'm gonna call them cluster variables, okay? So given this seed, all these cluster variables in this quiver, I can make a new seed by an operation called mutation, okay? And I'm not gonna give you all the details of mutation. It's very rigid and combinatorial. I'm just kind of gonna do an example. So to mutate, what you do is you pick a particular vertex of your quiver, like this one, 2, 5, 6, 7. And then what mutation is gonna do is first it's gonna change your quiver, but it's sort of only gonna change your quiver near this vertex, right? So here's the new quiver that I get, and you can see like all of this part looks the same, and there's just a little bit of change around the vertex where I mutated. And I should say exactly what change happens. There's like a recipe for it. I'm just not going to tell you right now. And then the other thing that happens is wherever I mutated, I'm going to change that cluster variable a bit. I'm going to replace it with some new function. And that function, I just read it straight off of the neighborhood, so the vertices around that vertex in the quiver. Okay, so in this example, I start with, I'm going to mutate it 2, 5, 6, 7. And I'm going to replace it with this new variable. How do I get this new variable? Well, 2, 5, 6, 7 is always going to show up in the denominator. And then the numerator is always going to have 2 terms. And so let's look at this term, 3, 5, 6, 7, 1, 2, 6, 7. The things in that term just come from looking at this quiver and seeing what points in to 2, 5, 6, 7. Okay, so one term over here comes from what points in. And then the other term over here comes from what points out. Okay, so that's a 1, 5, 6, 7, 2, 3, 6, 7. Okay, so the quiver tells you exactly how to update your cluster variable when you mutate. Okay, so that's our new cluster variable. And then you can use a Plücker relation to show that this is actually just another Plücker coordinate, 1, 3, 6, 7. So in this situation, so I started with this seed, quiver decorated with variables. I mutated, I got a new cluster variable, a new quiver, and it turned out my cluster variable was another Plücker coordinate. But I can perform mutation at any vertex of this quiver, except for the ones in boxes. And so I could also mutate at 2, 3, 6, 7. Again, the quiver changes a bit more this time. There's a concrete combinatorial rule for how it's changing. And then I get this new cluster variable by the same method down here. So again, I have 2, 3, 6, 7 in the denominator, because that's where I mutated. And then the numerator is these two terms, which I read just off of the stuff pointing in and the stuff pointing out. Okay, and then you can do some Plücker relations and show that what you get is this quadratic polynomial in the Plückers. So now that's your new cluster variable. Okay, I know this is, yeah, go ahead. Yeah, I want questions,
yeah,
please.
thank you. I'm curious, I mean, I'm thinking about this form that you define. It's a 5K form where these Fi appear. And now you're saying these Fi can be generated using mutations. I was wondering, I mean, for low n, I thought that there's only a finite number of cluster variables you can get from mutations. And so how does that, but on the other hand, for the form to exist, all of these Fi would have to be independent.
Yeah, so
how does that, how do these two come together?
Yeah, so the answer is, it's true that sometimes there are only finitely many cluster variables, but relatively rarely. So for GR4n, I think the only circumstance is like n equals 6 and n equals 7, and after that you get infinitely many.
Right, yeah. So 6 and 7, I guess you'd have, so for 7, I think 42.
Yeah, that seems about right.
6, I don't know,
Yeah.
maybe 9. I don't, does that match up with the,
And
maybe it does work out with the 5?
yeah, it does work out. In the end, right, so I say one of the things that I lied to you about is actually you only need, what you do, so you actually only need 4K things here. So what I should really do is I should sort of divide 4 of these by F1, and then another 4 by F6, and then another 4 by F, etc. So yeah, really I should only have 4K things here. But the other thing is the cluster variables I'm interested in kind of come from GR4n, and here we've got 4K, and usually K is much smaller than n, so really there is enough space. Yeah, okay. Yeah, so the difference between K and n, very important, yeah. Okay, so we've got some very precise and very rigid way to produce these cluster variables. And the way that you get the cluster algebra is you just do mutation forever. So you do arbitrary sequences of mutation. Yeah, you're allowed, yeah, you can do it forever. You usually get infinitely many seeds and infinitely many cluster variables. Right, and the point is, what does it mean for this ring, these polynomials and Plückers mod Plücker relations? Saying that that's a cluster algebra is saying all of our cluster variables actually belong in this ring. So even though there's division, when I define cluster variables, actually I can always use Plücker relations to undo that division. And I can really just honestly get a polynomial in Plücker coordinates. And the cluster variables, all of the cluster variables I see, they generate the ring. Okay, so yeah, so the thing that's really important to us actually is that mutation is going to stay inside of polynomials in Plücker coordinates. It doesn't leave that realm. Okay, so there are 2 more things I need to talk about. So, right, what have I done? I started with some ring that I knew was generated by the Plücker coordinates, and now I've just told you, okay, it's also generated by the infinitely many cluster variables. So that might seem like you've done a bad thing because you went from something where you had a finite generating set to something infinite. But the advantage of these cluster variables is that they're grouped together into these seeds. And that grouping is going to be important. So, 2 cluster variables are called compatible if they are together in some cluster, right? So in some seed. So as I mutate around, cluster variables are jumping out of seeds, jumping into seeds, et cetera. And so they're compatible if they show up in some seed together. Right, right, like 2, 5, 6, 7 and this y, those are compatible. And I want to focus on some special products of cluster variables called cluster monomials. So that's going to be any product of compatible cluster variables. Okay, so I'm sort of saying you can only, to get a cluster monomial, you can only multiply together those cluster variables that appear together in some seed. So if they never appear together, you're not allowed to multiply them. This is just a useful way of picking out some special functions on the Grassmannian. Okay, that's really what I'm giving you. I'm giving you a somewhat elaborate combinatorial rule to pick out special functions on the Grassmannian, special functions in Pluger coordinates. Okay, and these special functions are called cluster monomials. Okay. Let's see. Yeah, so one thing to say about them, they're linearly independent, so that's a nice thing. I'm not going to talk too much about this. Yeah. Yes, that's right, that's right. Yeah, so the ones in the blue boxes, so I kind of left this out. These are called frozen and you're never allowed to mutate there. So these are going to be compatible with every cluster variable. Yeah, so certainly if I take any product of the ones in the blue boxes, that will be a cluster monomial, and I could also multiply it by any cluster variable and get another cluster monomial. Yeah, in our circumstance, we're kind of going to want the interesting ones, these like higher degree polynomials like y that show up somewhere. Okay. Yeah, so maybe the like TLDR, the summary of this is I had this polynomials in Pluger's ring, and I identified in there some very special polynomials using a very rigid combinatorics of cluster algebras. Okay, so they have some, yeah, there's a lot of deep mathematics going down in here, which I'm not going to tell you. So yeah, for now we can just think cluster algebra structure is a very strong, like rigid combinatorial structure, and it identifies for us certain special polynomials. Okay, and the upshot for this, so why I told you about this is that these FIs, they are, okay, so I was telling you about GR4n, so Pluger's in GR4n. Let's just take that Pluger and identify it with this twistor coordinate, right? They both use 4 indices, so no harm. And the point is that these polynomials Fi that I use to cut out my BCFW tiles, they're very special functions. They're some cluster monomials for the Grassmannian. So they can't be arbitrary. They have to come up from this very rigid combinatorial structure. Yeah, go ahead.
For infinite cluster algebras, there are infinitely many cluster monomials. Is that right?
Yeah, that's right. So if you have a finite type cluster algebra, which means actually you only have finitely many cluster variables and clusters, you still have infinitely many monomials because you're allowed to take arbitrary powers of anything in the same cluster.
Then how does that help you to find these polynomials?
Yeah, so what we really want to do, so what we're really interested in is so these things won't be irreducible. Usually you can factor them. And so what this is saying is that when you factor them, the factors that you get will be just cluster variables, and they'll sit together in the same cluster. And I would say also, we have a version of this theorem that uses the cluster variables themselves instead of these cluster monomials. So in that situation, you can say, oh yeah, the tiles are cut out just by some compatible cluster variables having a specific sign.
Thanks.
Yeah, right. Okay, yeah, never mind, it's not that important. Right, okay, so why is this true? Well, the real reason is that the BCFW recursion is a very special kind of recursion. It preserves the cluster algebra structure, and that's what we show. Okay, and another very nice thing that this shows, so I have this tile in GR k plus 4, and I say, okay, how do I get my tile? I just ask that certain cluster monomials have a particular sign. How do I get to the boundaries? Well, the boundaries should be given by setting some things equal to 0, right? And so using this, you can show that actually your codimension 1 boundaries of your tile, again, they're not random polynomials. They have to be, the way I go to a codimension 1 boundary is I set some cluster variable equal to 0. And the collection of all codimension 1 boundaries, those cluster variables are going to be compatible, which is a pretty strong condition, right? They have to show up together in some seed. So this is sort of a sort of mysterious. I don't think this was, Yeah, there's nothing from BCFW that tells you that this should be true. So maybe to translate this back into like the original BCFW recursion, what this means is that, kind of assuming some things work as they should, the spurious poles that you see in those BCFW formulas, they're compatible cluster variables. So for some reason, this cluster structure on the Grassmannian is constraining the sorts of spurious poles that show up in these BCFW formulas. And as far as I know, we don't understand why that's the case at all. We just know that it's true because we proved it, but we sort of, yeah, we don't understand why cluster algebras like enter the picture from a physics perspective at all. Right, I should also say this sort of phenomenon where codimension 1 boundaries are cut out by compatible cluster variables, that's called cluster adjacency, or is a version of something called cluster adjacency. And this particular version was first conjectured by Drummond, Foster, and Gerdegan. And there's also a related paper of Magot, Schreiber, Spradlin, and Volovich. Okay, so yeah, so I guess what I should say is we didn't try to prove this theorem out of nowhere. It was noticed in some computations in physics like 7 years ago. And then, yeah, it turns out that it's true in general. Okay, and that's the end of what I have. Sorry, I think I probably sped up towards the end. So I have 4 more minutes. So this is a great time to ask questions or ask me to go back over anything if you're confused. I don't know. That's a really good question. I mean, they're called spurious because there's no obvious physical significance. So yeah, I don't know. I think I saw another hand. Yeah. No, infinite type. Yeah. Oh yeah. So I guess my counting was wrong. Sorry. Let me look at this seat again. Yeah, sorry. So there's a complete list of when this cluster algebra is finite type, and I think I just didn't do the right thing. So if you have GR2n, that cluster algebra is always finite type. Also, if you have GR36, and I think also GR37. Oh, okay, so maybe it is. And then the point is that there's a duality which switches k and n minus k. So this is the same thing as GR47. Yeah, so okay, yes, I guess this one is finite type. Yeah, this one is finite type. Okay, and then every other value of n higher than that is not, right? So I should say GR46 is also finite type because it's related by this duality to GR26. Okay, and then this one is finite, so that means this one is finite type too. Yeah, but then n8 and higher is infinite. Any other questions? Yeah. Yes. That's a really good question. So in theory, we should be able to do that. Actually, like writing it down really concretely, I don't know. Yeah, I mean, yeah, if you actually, yeah, what you'd need to do is you need to like do this recursive procedure, right, and write down your FIs across all of the different cells or all of the different tiles, and then you'd see, yeah, okay, we share two tiles share the same FI and have opposite signs, and so then, yeah, you should be adding those terms together in order to cancel that pole. Yeah, so I don't have a clever way to do it. Yeah. Mm-hmm. No negative. Yes, that's right. No, so not quite. So the smaller number that you need, is just actually the dimension of the positroid cell. So yeah, you can actually use cluster algebras to show this. So yeah, for each positroid cell, if you want to say what's the smallest number of minors I specify to be positive that force all of the other ones to be positive, it's it's the dimension of the cell, or like the number of faces of the Playback graph minus 1. Oh, so yeah, these were enumerated by Lauren Williams in her PhD thesis. I can't actually remember what the numbers are. I think if you, oh God, yeah, I think it's basically the Eulerian numbers. All right, there's my timer. But yeah, I couldn't quote you on it. It's on her website. If you scroll all the way down to the bottom of her list of papers, you know, from her thesis, then you can find it there.
Yeah, another question. In the infinite cluster type,
yeah,
is there some notion of how many mutations you need to find the Fi that appear in the formula?
So we do give an algorithm to find them all in the same seed together. I don't know how many mutations is in each step of the algorithm. Yeah. Yeah, but I guess, right, maybe that is a good thing to say. We're not just, it's better than just an existence result. We're not just saying there is a cluster where all of these things live in. We can actually we give you an algorithm to actually get to that cluster, which is pretty important, because if you just start here and you say, oh, I want to get to a cluster containing this cluster variable, it's very hard in general to do that. There's also some code which my collaborators have written, maybe using Sage, so not Mathematica. But yeah, I think that they've implemented this algorithm in Sage, and it's publicly available. Oh yeah, actually that reminds me. So not related, well, sort of related to the Amplituhedron, but if you're interested in getting your hands dirty, Jake Borgeli has a Positroids Mathematica package, which is available on the archive, like it's an auxiliary file for a paper that basically says, like, yeah, Positroids package for Mathematica, and it has a bunch of combinatorics of the totally non-negative Grassmannian coded in, and it also will do for you a random way of running the BCFW recursion. Not in momentum twisters, kind of in the original phrasing, but still, yeah, it can run for you the BCFW recursion if you'd like. Any other questions? Yeah. Yeah. Yeah, so with the same group, we sort of wrote one math paper and one physics paper. The physics paper has details about a non-BCFW tiling. So that tiling involves a tile called the spurion, so named because all of its facets are spurious poles. Okay, so this is a k equals 2, n equals 9 tiling, and m is equal to 4. Yeah, so this graph gives me a positroid cell upstairs. When I map it down with z tilde, I get a tile, so it's an injective map. But all of the facets of that tile are cut out by quadratics in momentum twisters, and the boundaries of the Amplituhedron are just momentum twisters by themselves. So this tile, however it sits in the Amplituhedron, it completely avoids the boundary, and that's just never true of a BCFW tile. So yeah, I showed you, right, in this recursion, for our FIs for the BCFW, we always have these 5 twisters, and one of them, I think this one is actually always going to be a facet, and it actually is a facet of the Amplituhedron as well. So BCFW tiles always sort of touch the boundary of the Amplituhedron, but this tile does not touch the boundary. And so, yeah, if you cook up some formula for the scattering amplitude using this tile, all of the contributions from this tile will disappear in the end because it kind of only contributes spurious poles. For what it's worth, we don't expect this to be like a special phenomenon to k equals 2, n equals 9. We expect it to continue kind of, forever. As soon as you sort of pick up one thing that looks like this, you should be able to get more and more and more. Yeah. I'm sorry. Is there a minimum number? A minimum number to cover the whole thing? Is that what you're thinking? Right. This is a very interesting mathematics conjecture, actually, that every tiling of the amplituhedron should consist of exactly the same number of tiles. So in some way, there's a minimum, but it's a bad minimum because it's the number of tiles you need no matter what. Yeah, this is a very interesting math conjecture. It means, like, one thing that's definitely right. So it sort of makes you think that there's something actually like volume, where each tile has a constant volume, and so then, and your amplituhedron has some volume, so you just need a certain number of tiles to cover the whole thing. We haven't figured out anything like that, but that's, yeah, sort of the idea.
Maybe a bit of a concrete, practical question. Let's say you had two different tilings and you computed then the canonical forms. So you have two canonical forms and you suspect whether they're equal. Are there any tricks how you'd go about this?
Oh, I'm not the person to ask. Yeah, I'm definitely not the person to ask. I mean, if you proved that a lot of things were positive geometries, then I think it would be sort of guaranteed, right? So if things are actually canonical forms, then I think this is part of the structure of positive geometries. But if you don't know that they're canonical forms, you just have the forms and you hope that they're equal, yeah, I do not know. I wish I did.
Do we have more questions, or is it time for tea? I do not see.
That means tea.
I didn't see more questions. So let's thank Melissa again for two fantastic lectures.